Case 2. We have done our long division step. We have our proper rational function. We factor the denominator. And what do we get? Q of x is a product of linear factors, and some of them have repeats. What do we do? That's okay. So let's say that this term, a1 times x plus b1, is repeated r number of times. So what we're going to do is, if r is the exponent associated with this factor, that factor is going to have r many fractions. That's it. So an a1 divided by the linear term, an a2 divided by the linear term squared, an a3 divided by the linear term cubed, and so on. We can just keep going. I mean, the algebra can keep going. I probably won't make you do more than like 10 of these. So let's do this as an example problem. Here is my x cubed minus x plus 1. That's degree 3 on the numerator. And here is my x squared times x minus 1 cubed. That is a degree 5 on the denominator. And they have been so kind as to write it in factored form. Now, the linear term x by itself is repeated twice. So it needs two separate fractions. We will call that a capital A on x plus a capital B on x squared. The x minus 1 term occurs to the third power. So we're going to need a capital C on x minus 1, a capital D on x minus 1 squared, and a capital E on x minus 1 to the power 3. Okay, so we got 5 different fractions. You know, not that bad. We can do this. But, you know, for a case of showing how this works, let's go ahead and do something a little easier for just this time. Here's one that's a little bit easier. So here's our integral. The rational function in the integrand is x to the power 4 minus 2x squared plus 4x plus 1. We're going to divide that by the polynomial x cubed minus x squared minus x plus 1. So 4 is a bigger number than 3. Surprising. That means we're going to have to do our long division step, which again, they have explained very nicely for us here. We get a quotient of x plus 1 and a remainder of 4x divided by that very same denominator. Okay, so now we got to get to the factoring step. Now, they're saying since q of 1 equals 0, we know that x minus 1 is a factor. Is that right? So 1 cubed minus 1 squared minus 1 plus 1. Sounds like 1 minus 1 minus 1 plus 1. Yes, sounds like 0. Okay, so yes, x minus 1 is a factor. What's the other term we get? X squared minus 1. Again, there is my very nice difference of squares factorization. So I can rewrite this as x minus 1 squared times x plus 1. There's my repeated factor. Okay, so in this example, we only have 3 fractions to worry about. Again, the x minus 1 is the repeated factor, so it has 2. It has 2 rational functions associated to it. Capital A divided by x minus 1 and capital B divided by x minus 1 squared. So how are we going to solve for all that? The very same way we did on the last time. We're going to multiply through by the denominator, which is x minus 1 squared times x plus 1. How do I know that's the right one? It's the denominator on the left side. There it is. That's what I'm multiplying by. So when I do that, some of these denominators will cancel. Some of them will have leftover stuff attached to them too. That's fine. But I can perform my algebra. I can multiply everything out. Left side is a polynomial, right side is a polynomial. So it's a polynomial. So 4 times x equals, polynomial something times x squared plus something times x plus something. You know what that tells me right off the bat, like immediately? A plus c equals 0. It just has to. There's no x squareds on the left. So there can't actually be any x squareds on the right either. Same thing with the constant term. There's no constant term on the left, so negative a plus b plus c has to be 0. And that means that b minus 2c has to be 4, right? This is the intuition for setting up these kinds of algebra problems. So there's exactly what I was saying. There's a system of equations, and we can solve that. So I'm just going to leave that out for this lecture. Those are our coefficients. And what have we got? This integral is going to be equal on the second line. There's my quotient. Here are my linear term, gives me a 1 over x minus 1, and the 2 over x minus 1 squared. Okay. And then subtract off the 1 over x plus 1. All right, cool. So antiderivative is x squared. Antiderivative is x. I should be saying that out a bit in more detail. Sorry. Looking at the parts of this function, I can find those antiderivatives. So the antiderivative of x is x squared divided by 2. Antiderivative of 1 is x. Antiderivative of 1 divided by x minus 1 is natural log of x minus 1. There's some implicit u substitution stuff. We start to get a little bit more intuitive feel for these kinds of functions. Here, on this term, 2 divided by x minus 1 squared, that's another u substitution. U equals x minus 1 squared. So the antiderivative is minus 2 on u, which is minus 2 divided by x minus 1, right? Those are the kinds of details that I'm starting to do in my head since I am moving on to more advanced integration techniques. Doing them on the scratch work is also fine. And again, integral of negative 1 divided by x plus 1 is minus the natural logarithm of x plus 1 in absolute values. And there's our constant integration. And I see that whoever wrote this slide decided to combine those two different natural logs. This one is a plus, this one is a minus. So my logarithm formula says we're taking the logarithm of a rational function. But that would be the integral.